And Vlodek, please stay with us for the discussion panel. If you don't mind leaving your camera on, you'll be on the screen.
Okay, all right, yes.
While the other panel members, it's Ilya and Maria Papa. Maria Alessandra. Two chairs, thank you, Natalie. Oh, yeah. I'll keep this one. All right, so we have about half an hour for discussions, and maybe I can start with whether some people have pressing questions that they could not ask either Vlodek, Ilya, or Maria Alessandra before. We could start like this. If not, we have some discussion topics. Then yes, please go ahead. Natalie threw you under the bus, so now.
Yeah. Right? Yeah.
Yes.
Well, yes. So suppose from an old sky search, I have a candidate surviving. That's not a hardware injection. The first thing we typically do is look it up in the ATNF catalog. Suppose we don't find anything. We're gonna ring up our favorite radio astronomer and X-ray astronomer friends, and they might be able to do new observations or start looking in archival data. Because you see, once we tell them the precise location, they can in turn perform more sensitive searches. What else should we be doing? And is there something we should be doing before we find ourselves in that situation to sort of get ready?
Question for everyone. Does anyone have the answer?
So I don't have the answer. But do you actually have any information about the source other than just the frequency? There's no other, well, and the position as well, obviously. But right, okay. So you've got maybe some idea about what the source nature might be.
Well, a neutron star.
Yeah, but I mean, I guess you would know if it was in a binary.
Oh, yes, of course. I could definitely tell you whether it's in a binary. So the source parameters, like the binary parameters, but let's, for simplicity, assume it's an isolated object. Okay. Because those are the most extensive and sensitive searches that we do.
And you've got a really good position. So, I mean, things like optical spectroscopy might be handy just to have an idea about what the object is. But, I mean, if it's a single...
How far can you go with optical?
Yeah, so if it's a single...
And it's full, right?
Yeah, if it's a single object, then it's going to be really difficult to probably detect it in optical. But that's why I asked about the binary thing, because, yeah, then if you've got maybe some hope of some kind of accretion, then, yeah, you might be able to get a spectrum even out into another galaxy without any problem.
For isolated and cold neutron stars, a couple of 100 parsec maximum, and maybe with the ALT a bit more, but that's going to be the limit. You would know the distance as well precisely, or? No. Okay.
I mean, because the deformation and the distance are degenerate. I could either make the deformation larger, which means it could be further away, or I could make the deformation smaller, and then it would need to be closer by to give the same gravitation wave signal.
Okay, so the EM observation could actually help you quantify the distance a little bit and then quantify the deformation. Okay. Yes, there's a question behind or a comment.
Follow up a little bit. Maybe we can also think about synergies with Lisa. I know it's far away from now, but right, we will have some neutron stars, unfortunately, in binaries, but we will measure frequency and frequency derivatives, sky locations. Maybe there is some overlap between continuous LISA and high frequency searches. Yeah.
So, in fact, back in the days when there were the mock data challenges, we actually, for the galactic white dwarf binaries, we did use our techniques to detect the continuous waves in LISA and performed quite well. So I think would like to think about that problem again once we get close to actually there being more data, real data.
Any comment? If not, I'd like to continue on. I wanted to ask your, sorry. Oh, my bad. I'll keep this one and you can.
Yeah, and just a quick comment on that. I guess those sources could be multi-band gravitational wave sources, right? Like presumably Lisa would be seeing maybe the binary orbit, the gravitational waves from the binary orbit, and then if you have one of those neutron stars, for instance, having this ellipticity, then ETCE would be seeing then the gravitational waves from the single source, and so then you'd have like a multi-band kind of detection then. But I guess what are the odds of that though? If you have, let's say, two compact objects in a stable binary.
So, a single, unless it's a magnetar with a huge magnetic field, at those low frequencies, even with ellipticities of 10 to the -5 or 10 to the -6, not going to see much because the amplitude scales quadratically with the frequency. So the same deformation gives you a lot more signal at higher frequencies. So down at lower frequencies, you're very penalized.
Yeah, but I mean, with the LISA frequencies would be detecting the orbital.
Yeah.
Right. And so, but then if you have one of those objects having an ellipticity.
Yeah, and I say, so
depending on how
waves
fast it's
from
spinning.
that ellipticities are going to be very weak. Unless that's spinning very fast, which I would imagine probably not. Since it's not recycled, since it's still in its orbital, it's still orbiting out.
If there's no other comment on this, I just wanted to ask your opinion about whether you think the first detection of a continuous gravitational wave will come from a blind search where you potentially have a lot of sources, or from the targeted search on the handful of pulsars that we are, for which we have a limit below the spin down limit.
Good question. I actually think it will come from a category in the middle, which are the directed ones. So we know where to point, but the accreting ones, that's what I would imagine.
Any particular reason why you expect those?
Because there is evidence that there is something that's in LMXBs not making these objects spin to higher frequencies than the accretion would suggest. And gravitational waves are a very effective mechanism to produce that. And there is a way to produce, for sure, that asymmetry through the accretion.
Yes, okay.
So, of course, there's then, and Sylvia knows a lot about this, there's the unknowns, not neutron stars. We could detect a continuous wave, not from a spinning neutron star, but from more exotic scenarios, boson clouds around black holes. There could be signatures of that. You're detecting a continuous wave. There's absolutely no electromagnetic counterpart. And if anything, there's a slight spin up. That's going to be a tough one to, first of all, to believe that it's not, we'd have to observe it over and over to really get us thinking along those lines.
And if there's no electromagnetic counterpart,
No,
there's no support that the observers on the EM side can bring. No?
Exactly. But I mean, it would still, in order to know that there is no EM counterpart, you need to look.
Yeah, sorry.
Yeah, but just to add on, I guess in principle, though, if we're talking about axion clouds around black holes, in principle, there could be a very weak, I think either X-ray or radio signal for if the black hole is in a dense enough region and it creates and yeah, but I mean, the chances of this are also, I think, pretty, and I don't think we have the sensitivity right now anyway to be able to find something like that.
With the, for the EM signal.
Yes.
Perhaps our other panelists, Vlodek and Ilya, have comments?
Yes, if I may ask a question also, like, are these continuous wave searches confined to radio pulsars, or do we also look at X-ray bursters, the accreting neutron star sources, which also rotate presumably at very short periods?
So the searches are carried out for any object that spins, let's say, in a frequency consistent with gravitational waves in the LIGO band, and for which we have precise enough ephemeris. And it's not just radio. In fact, the Einstein at Home project also looks for to discover new pulsars in X-ray and gamma ray data. And we started doing that exactly to provide targets to the continuous wave searches. And it had discovered a number of pulsars, so also X-ray and gamma rays. And then, for the targeted searches, as long as one has precise enough ephemeris, these are used. And there's about a few hundred objects.
Thank you.
Is there anything we're missing from the EM side that could help those searches?
Yeah, please continue to look for pulsations from the CCOs in young supernova remnants and in Scorpius X1. That would be great. In the absence of pulsations, give us the most, for Scorpius X1, the most precise orbital parameters that you can. It means that we save compute cycles to look for different orbital parameter combinations, and we can broaden the frequency range.
Anything to shrink the parameter space, basically.
Yeah.
Okay. Anyone working on this on Scorpius X1?
So observing pulsar glitches, that's useful to know when they glitch.
Yeah, maybe we can move to something like Lisa as well to talk about continuous waves, because obviously the kind of source you talked about, I guess, is going to be a continuous wave source in Lisa. Do you have any comments on that, like looking for these kinds of objects?
Yes, that's something I can talk more about. So for this, we need, as I talked about, and we need continuous observations of basically the whole sky, or at least of a huge part of it in different wavelengths, so that we see if we see such objects or similar objects, that we really have a continuous light curve, which should be complete on also in the if I come back to my specific source, that even in the quiescent state, that we have also data which we can use for our to assess whether it's what it was doing, basically, like this.
Are there other types of sources that could emit continuous waves? So we talk about the black holes and the neutron stars, but other white dwarfs, yeah.
Yes, obviously, this is the prime Lisa target, white dwarfs.
But in binaries.
In binaries, yes,
in
in
binaries,
binaries, yeah. Mhm.
Any comment? Any other question?
Maybe a question for continuing for the white dwarfs to the audience also. Can we be certain to see such sources in gravitational waves? Or how certain can we be that we really detect something and it's not just noise or an overlap of different other sources?
That's a question for global fit people, I guess.
Well, if I may make a general comment, I think when you have a continuous wave, it's very hard rather very easy to distinguish it once you observe it from noise, right? You have different segments of data, and that's a reproducible frequency.
Yes, I'm going to basically repeat what Antoine said, what Peter said earlier, that we are helped in distinguishing, for instance, a quasi-monochromatic signal from pure noise artifact. We are helped by the fact that LISA is moving. So you have the whole motion of LISA, the orbital modulation, but also the main Doppler phase of the orbiter on the sun. That leaves a distinctive imprint on the signal, right? If you had a noise artifact that would look like a line, we don't expect many. We cannot say never, but we don't expect many line artifacts like we have in LIGO vehicle. But if you had one, it would not have these features. So this is a fairly robust way of directly telling apart what is a gravitational wave signal and what is not. The difficult problem, however, is confusion with other gravitational wave signals. That will be here anyway, and at some point it becomes a fairly complex problem because so these modulations are very distinctive, but in a sense, they broaden the signals, they give it an extended bandwidth, so it's not only monochromatic anymore. But then at some point you start, in a given very narrow frequency band, you start to accumulate, to superpose 8, 10, 20 signals with each other. At some point you have confusion. So you start to have alternative scenarios of reproducing the same signal you see with different set of solutions of 2 binaries or 3 binaries with different parameters. And this is always going to be a limit. So as you go down in a scenario, we're going to be really confusion limited in a wide part of the frequency band. But the loudest binaries will be extremely clear, will be extremely easy to interpret as gravitational waves. That's for sure.
Someone wants to jump on this, or we change topic maybe? We have still a bit of time. And maybe I wanted to address a question a bit vague about the computational power that is needed for this. I mean, you showed us that you have to distribute with the Einstein at Home project. Is that the only solution, or we can expect in the future to use new techniques? I don't know, maybe even quantum computing. Not that I know anything about it, but
it's always easy to invoke some magic that's going to happen in the future. So one of the things that a number of people are looking into is using machine learning techniques. However, it's interesting because in order to work and help the detection problem, they have to be tuned in a rather different environment than where they typically work well nowadays, in two ways. One, typically, imagine image recognition. First of all, there are localized features that these algorithms kind of attach themselves to. And so they're localized in space. They are hence visible, which means relatively high SNR. And then these are good at refining and building on these. And also they are local. Our signals are very weak and, you know, span, they're not localized in time either. They're very weak, and that's the problem. It's a completely different regime. I mean, there's papers that show improvement, but basically it's been shown that convolutional networks are not very effective, even though we've basically now matched the match filter performance, some time baselines of about 10 days, which is not bad for old sky searches. But, you know, we got to bridge the 1 year timescale. And so it seems like transformers are better, but these are black boxes. So it's very time consuming to understand. And even when you think you've understood what's really happening, then you run it on a different set of parameters and something unexpected happens. So it's frustrating, and I don't know. So we do need some new ideas. I'm not quite sure what these will be. I'm not, you know, there's people very enthusiastic about machine learning.
Yeah,
Perhaps that will do it.
for now, the brute force is the safest, most reassuring way.
Well, at least, you know, data is coming in and somebody's got to look at the data.
Yeah. Any machine learning expert to comment on this? Or another topic? Well, Natalie.
Yeah, it's only an extension of a topic, but I don't know if there's anyone else left in the room. So PTAs, by excellence, do continuous gravitational wave searches. Does anyone want to comment on looking for these continuous gravitational waves? If there's anyone left in the room, there's a few people. Maybe. I mean, the difficulties, the improvements that's going to be done, and to be able to get to sources like Ilya's source. You said it was too faint for the PTA, I think. I mean, it's the right mass, if I remember.
There's also, but the question is, even if we have a source that would, in theory, be detectable by PTAs, and this is again a question in the room, it won't be distinguishable in the gravitational wave background, because the frequency, you have to observe it over many years, of course, to have a nice to see many periods of the same system. And then my guess is that it's just too hard to distinguish the source from the background that you have. But PTA people may say something different, but this is my view on it.
Yeah, I mean, if you've got an approximate frequency and you've got a mass and stuff like that, they can put that in and then they can look for that specific kind of object within their data, and it does improve the signal to noise. And that's the kind of thing we've been doing with the objects that Vincent's been identifying. So yeah, I think you probably could do something. But yeah, I'm not a PTA person.
No rush.
Yes, and I guess in that case, then not only you would have the physical properties of the source, but you would also have the sky position. Does that help PTAs if you have a sky position as well? Okay, yeah, Yeah, so presumably then this would be, you would be able to do a deeper search then for your source or for a given source then.
So perhaps I have a comment, which is continuous waves are clearly not yet been detected. And if I think back what happened at the first detection of a gravitational wave signal, was that the detector configuration was frozen and a whole bunch of checks were made to make sure that, you know, we understood really what was going on in those detectors. Now, with continuous waves, right now you have to have, first of all the data in the can, and then you start analyzing it. Which means that by the time you finished your analysis, possibly the detector barely exists anymore in the configuration that it produced the data. And not to get back to the same problem, but for the people who only get the data with an extra 2 years of latency, the detector is for sure not there anymore. And so if we do detect something, I want to say that because of the latency in the data release, those checks are going to be even harder. And that's something that I worry about. Because they're not going to be able to make the measurements to know, could there have been some coherence, weird, can we test? That's going to be impossible. It's true, there's lots of checks that one can do with using the astrophysical signature of the signal. But there's nothing more reassuring of having some direct checks on the hardware as well.
On your right.
Just to follow up on that, I mean, are these data releases complete enough for your kind of external data analysis, or are there one of these witness channels of noise, additional noise things missing, or is this fairly complete and you're happy with that? Or?
We're happy. We're happy. They've been enhanced with all sorts of auxiliary channels back in the last release. And also the collaborations do some cleaning. And they've released also the unclean data plus the witness channels they use for the cleaning. So that side is is good.
Sounds then like a good example for the other collaborations, for the continued discussion on data releases and how to organize that.
I mean, some of us on the outside would be completely happy to help with that if help is needed. We just don't want to have to be involved in the whole.
Thanks. Were there any LVK people here to hear that? Yeah. The message is taken. No, we were talking earlier on, actually, maybe it might be an idea to write a short, I don't know, summary of what's gone on this week, because there's been some really interesting suggestions. So maybe write a small proceedings, maybe something we discussed a little bit earlier on today. So yeah, I've just noted that down. Maybe we can put that in there too. I mean, something should come out of this meeting. I mean, it's good for training, but it's also good for bringing up new ideas.
I have a few minutes left if there's another topic to discuss. Yes. Yeah.
I mean, this is kind of not quite aimed at the panel, but I guess about the top, the question of what comes out of this meeting. I'm very ignorant of this. Are there any efforts to gather sort of, to create a meeting or workshop for electromagnetic counterparts to LISA signals? Just to discuss, because this came up before, right? Like what does the LISA community want from the electromagnetic folks? And so could we have a workshop or something to discuss that more in person? Okay, let's do it. Okay.
The answer was yes from Natalie. Any last comment from the audience, from the panel? No? Then I think we should thank, oh, sorry. No? Okay. Then we should thank everyone again, Maria Alessandra, Flodek, and Ilya for their answers, and you for the questions and the comments. Thank you.
Thank you all.
And so we have, I forgot, 20 minutes, 30 minutes coffee break.